So for the last 11 miles or so, I've been hiking across flat land here, across the LA Basin. Now after telling you that the hills down in Long Beach and Signal Hill are a result of active faulting and potential earthquakes and folding of the ground, you might be thinking, well, flatland, that's got to be good news. That's got to mean there's no geologic hazards here. Unfortunately, to a geologist, all this flat land here is a pretty sure sign of flooding. So, in a tectonically active place like Southern California, flat land isn't really the status quo. To get flat land, we need some sort of active geologic process. And generally speaking, in Southern California, that's going to be flooding of some sort of river. Now, if you're from Southern California, you might be thinking, wait a minute, there aren't any big rivers in Southern California. All we have is these piddly concrete-lined streams. How's that going to cause major flooding? And, well, there's a big story behind that, but basically, if we were to go back prior to about 100 years ago, before there was a city here, these rivers flowed free across the landscape, and they changed their banks from time to time. Here in Southern California, the climate is dry and sunny most of the year. That's why people like to live here. But in the winter, occasionally there are big storms. You know, although the annual rainfall here is only maybe 10-15 inches a year, some of these big storms can put out that much or more in a single storm. So when all that rain comes at once, it falls up in the mountains way up that way. I don't know if we can see it, too many clouds today. But that leads to huge flooding events coming down these rivers. Back, you know, in pre-colonial times, the Tongva people respected the active lifestyle of these rivers and built their villages on high ground. But once Henry Huntington put in his electric train lines, people started building houses all over the LA Basin, all over all the areas of flat land. And then when we started having more floods, there's a big flood in 1914, 1934, and 1938. Those big floods all caused massive damage because they're now houses built on that flat land. Now, the biggest flood in the historical sort of post-colonial period was in 1862. There was a massive flood where it's said that the San Gabriel River here, and also the Los Angeles River and the Santa Ana River, which are the three main rivers in the LA area, they all flooded at once. And the water covered basically the entire LA Basin to a depth of a couple feet. It said that you could take a canoe from Venice Beach all the way to Huntington Beach because the entire coastal plain of the LA Basin was completely flooded. So at that time in 1862, this was primarily an agricultural area, so it didn't really do that much economic damage. I mean, it definitely wiped out some people's homes. But if something like that, again, were to happen again today, it would be devastating. You know, if we look at the amount of water flooding through the channel right now, or I shouldn't say flooding, going through the channel right now, like, I don't know, that's maybe 10 cubic feet per second. It's hard to estimate, I'm not a hydrologist, but ballpark, probably something like that. In these massive rain events called atmospheric rivers, basically if there's a massive amount of humid air that's funneled across the Pacific Ocean, comes and hits the mountains and dumps out all that rain at once. During one of those big, you know, 100-year storms or 500-year storms, you could potentially have more like 100,000 cubic feet per second coming down this channel. Except this channel isn't designed to hold 100,000 cubic feet per second. So that would be a problem. Now, to mitigate that, after the big storm in 1938, they built a couple of big flood control dams upstream. The two most notable ones are the Santa Fe Dam and the Whittier Narrows Dam. We'll talk about those later. But before these rivers were channelized, they used to meander all across the landscape basically each new flood would change the course of the river, and it would flow a completely different area, such that over geologic time, over the scale of hundreds to thousands of years, the rivers would sweep back and forth across the entire coastal plain. In fact, for those of you guys who live in West LA, Bayona Creek, or Bologna Creek if you prefer, is actually the former course of the Los Angeles River before that 1862 flood. And then in 1862, with the big flood, it switched from flowing out to the west, south of Santa Monica, in the Venice Beach area, to flowing south to the San Pedro area where it flows now. So, you know, again, to a geologist, you see this big flat landscape, it implies a very dynamic activity of rivers sweeping back and forth in a very active way, which is not really very consistent with the way we built it up with houses. Just to give a shout out to golf and stuff. This place has been around since I was a kid. It's like locally pretty famous. I think like there's a scene from Karate Kid filmed here. That is all. Okay, made it to Santa Fe Springs. It's time for lunch. Last time I like tried to bake my own bread and eat food that was semi-real food. This time I'm just leading into you know, whatever processed foods I can find, catch as catch can along the route, because I'm not getting anyone to supply me before I get there in 2 weeks, so it's just gonna be whatever stuff I can find at fast food and convenience stores along the way. But a little fried chicken sounds pretty good right now. There's a decent amount of water up in this part of the San Gabriel River. It must have had some rain or snow up in the mountains recently. They put these dams here so the water backs up into these sort of shallow lake-like things, and that helps it seep into the groundwater to replenish the groundwater supply. Although Los Angeles and neighboring cities import about half of our water, the other half comes from locally sourced groundwater, which is a significant amount of which is replenished by these kinds of catchment basins. Okay, after walking up about 23 miles up the San Gabriel River here, we finally come up to a place where the views are from hills. So far, the last 23 miles basically all flat. Here we come up to some hills that rise fairly abruptly out of the flat plain. We just climbed up onto this railroad embankment just to get a better view. And so the front of those hills there is because there are some active faults. This is generally true in California. If we have hills, usually it's because there are faults nearby. In this case, there are actually two faults. The one right at the right side of the hills is something called the Whittier fault. That fault is sort of similar to the San Andreas fault, and is what we call a right lateral fault. So the stuff on the far side on the left is moving away from us to the right at about 2 to 3 millimeters a year, and the side we're standing on is moving north about, relative to the other side, about 2 to 3 millimeters per year. Now, in addition to having some strike-slip moment, so a horizontal movement of the ground like the San Andreas, this fault also has an uplift component. So the hills are also being pushed up a little bit every time there's an earthquake. In this case, there hasn't been any recent large earthquakes on the Whittier fault. Based on paleoseismic work looking at sort of how sediments have been disrupted by previous earthquakes, it's been suggested that there's a big earthquake here about every 1700 years or so, plus or minus, and that's about the same amount of time as the last earthquake, which doesn't mean that we're necessarily going to have one imminently, because that's not how earthquakes work, but it does mean that one could in theory happen at any time, with like a 1 in 1700 chance per year, roughly speaking. Now the size of that earthquake is probably, we're talking in the 7 range for one of those quakes. Now the Whittier fault here that goes past the right side of that hill actually continues and connects up with another fault called the Elsinore fault. So together the Whittier-Elsinore fault extend almost all the way down to Mexico. In fact, they might link up with another fault called the Laguna Salada fault in Mexico. So depending on how much of that system breaks at once, we could have up to a magnitude 7.8 earthquake, which could be quite devastating. Now it turns out when earthquakes rupture, the direction they break in determines which way the energy goes. So if the earthquake starts, had an epicenter in the northwest and then ruptured towards the southeast, that would push a lot of the earthquake energy away towards Mexico, and it wouldn't be quite as damaging to Los Angeles. It happened the other way, where it broke down further south in California and then propagated towards the northwest this way. That seismic energy would come right over this way directly towards downtown Los Angeles, which is just a few miles that way now. Well, several miles that way now. So that could be potentially very devastating, especially if it was a magnitude 7.8 earthquake. So it's not just the San Andreas Fault we have to be worried about, although of course earthquakes like this would be not as frequent. Now, if you've been living in LA for a long time, you might have heard of the Whittier Narrows quake that happened in 1987. That was a magnitude 5.9 quake that happened near here. This area here is actually called the Whittier Narrows because the San Gabriel River is on a broad, wide plain up to the north, and it narrows down to a relatively small corridor here where it passes between the Hacienda Hills here and the, I don't know, I forget the name of the hills on that side, but it comes through sort of a narrow spot. So the Whittier Narrows Fault, it turns out, was not on the Whittier Fault, but on the other fault I alluded to, called the Puente Fault. So the Puente Fault would be further out to the right, and it's a different kind of fault. So the Whittier Fault is a strike slip fault. It's not quite vertical. It's actually dipping a little bit off to the left, to the northeast. The Puente Fault, on the other hand, is what we call a blind thrust fault. And so it's, first of all, a thrust fault. So it's dipping much more shallowly, more like 30 degrees to the northeast. So that would be off to the left. And it's also a blind fault, meaning it doesn't come all the way up to the surface. It ends before it gets to the surface. So this is the same kind of fault that the Northridge earthquake happened on in 1994. Because it's a thrust fault and fairly shallow in that orientation, it has a large surface area of the fault that's relatively close to the ground. So it would cause potentially very strong shaking throughout the urban area around here. So in addition to the 1987 Whittier Narrows quake, there was also a magnitude 5.1 earthquake in 2014 in La Habra, the La Habra quake that some people might remember. That was also on the Puente Hills Fault. Now, the Puente Hills Fault is a complicated system. It has a bunch of these different segments that come in, sort of step over from one another. It's not entirely clear how many of those segments would rupture at once. There are also similar thrust faults that continue over to downtown LA, which you can't really see from here. But if you've been to downtown LA, you notice it's kind of hilly there. Those hills are also been uplifted by blind thrust faults similar to the Puente Hills Fault. Again, it's not clear if they would rupture at the same time as the Puente Hills Fault or not, but it's definitely downtown LA is susceptible to the same kinds of earthquakes. Based off of paleoseismic studies, it's thought the Puente Hills Fault as a major magnitude 7.2 to 7.5 earthquake about every 2,500 years or so, and that could also happen, basically at any time now. Although again, the probability per year is fairly low. If there was one of these blind thrust style earthquakes, say underneath downtown LA, in addition to having potentially violent shaking, another side effect is that on these blind thrust faults, when the thrust fault slips up, the rock on top of them actually get folded up a little bit and tilted. And so it's possible that some of the skyscrapers in downtown LA could be permanently tilted a small amount, which I just hope the several engineers thought of that when they designed those buildings. So the Puente Hill Fault is actually to the right of the Whittier Fault, and so although it's probably partially responsible for uplifting the Hacienda Hills and Puente Hills over here, it's also it would daylight closer to where like the La Habra Hills and the hills to the south of those are. So it extends further to the south. Okay, I'm gonna get down off this rail embankment before another train comes. The train actually was passing by right before I got here. So right here we're looking at the San Gabriel River as we're coming up to the Whittier Narrows Dam. So the question is, here you can see that there are these big gravel earthen banks on both sides of the river to help keep it into a channel so it can't escape and flood the countryside. There's a horse over there. And there's this big dam here, the Whittier Narrows Dam, built to help stop floodwaters too. So is that good enough? Well, it's a good question. If you look at the width of this channel, it's really quite wide. You could imagine that could carry a lot of water. But it turns out the amount of water there was in a big flood in 1862 was somewhat bigger than that. You could say, well, okay, well, this channel can't quite hold all the water from the kind of flood you'd expect. So that's why they build these massive flood control structures like the Whittier Narrows Dam here. But are those going to be able to hold all the water? So this is where we need to get a little bit technical. So when people talk about the size of floods or the flows of rivers, usually talk about it in cubic feet per second. So cubic feet per second is just imagine a box of water, 1 foot on each side, and one of those passes by each second. Now, when we're talking about massive floods, or say the amount of water we can hold in behind a dam, people often talk about it in terms of acre feet. So an acre foot is an area of land 1 acre in size, flooded 1 foot deep. Now an acre is about 43,000 square feet, so that means that an acre foot is about 43,000 cubic feet. So an acre foot per second, if we're talking about flow rates, would be the same as about 43,000 cubic feet per second. So this channel here behind me for the San Gabriel River, right in this location, I think can hold something like 70,000 cubic feet per second, which is a little less than 2 acre feet per second. And that's about the amount of water predicted to come in what they call the 100-year storm, which is a little bit of a misnomer. I'll talk more about that later, but the original idea between the terminology 100-year storm is it's the biggest size storm you could expect to see in 100 years. Or to put it a little bit more accurately, you'd expect to see, you have a 1% chance of getting a storm that big every year. Okay, so if the channel can hold the 100-year storm, okay, that's great. But what if there's a bigger storm? So it turns out the every 500 years or so, the expected 500-year storm would have a flow that would be more like 120,000 cubic feet per second, which is about 3 acre feet per second. Well, that's now bigger than the channel can hold. And also, I will say, the channel right there will hold about 70,000 cubic feet per second. If you go downstream, there are a bunch of places where it actually won't hold that much. So actually, even for the 100-year storm, trying to channelize the San Gabriel River gets just a little bit sketchy. But if you think about rarer storms, like the supposed 500-year storm, or we could talk about, there's this big storm in 1852. So if we had a repeat of flood of that, that would be probably even more than 3 acre feet per second. I couldn't find a real great estimate for that just in a quick search online, but you know, maybe it'd be 4 or 5 cubic feet per second. That would be, you know, far in excess of what the channel could hold, even in the best patches of it. So then the question is, okay, we have these big dams here. Can these hold these things? So there's 2 big dams out in the basin here. This is the Whittier Narrows Dam. It was built in 1957, or at least it was finished in 1957. If you go a few miles up that way, there's the Santa Fe Dam. So both of those can help store water to help, or, you know, reduce the risk of flooding. The Santa Fe Dam can hold back something like 40,000 acre feet of water, and this dam can hold back something like 70,000 acre feet of water. But if you start doing the math with flow rates of, you know, a few acre feet per second, then all of a sudden, you know, a capacity of, you know, 40 to 70,000 acre feet is something you can fill up in, you know, a matter of less than a day. When the giant flood of 1852 happened, it rained for multiple days on end. So you could imagine a scenario where the water is running too fast to let it go through the channel without flooding, so they start storing it in the dam, but then it just keeps raining, and then you know, whoever is, well, the U.S. Army Corps of Engineers built these dams, so they're responsible for their operation. So there might come a time, if you have one of these big floods, where you're going to reach some tough decisions. So if the question is, you know, are these dams going to hold in the case of a massive flood? There's a scenario that the USGS came up with called the arc storm, which is a hypothetical flood, like the 500-year flood, basically. And so the Army Corps of Engineers looked into this, and the answer is the Santa Fe Dam up that way is, in a big scenario like that, is either unsafe or potentially unsafe. And this dam, the Whittier Narrows Dam, was rated at the lowest safety rating they have. And so it's, you know, basically it's not clear if these dams would be safe in those sort of massive flooding scenarios. You know, basically there are a few things to worry about. One is earthen dams like these aren't really meant to be filled. If you fill this dam with water, the water starts percolating through the dam. and there's some risk of the whole dam basically liquefying and washing away, or having channels of water percolate through the inside of the dam and then weaken the dam from the inside. You know, in a hypothetical major flood event, you know, there are different scenarios we could have. One might be just the dam is filling too fast that they're worrying about it overtopping, so they have to release water very rapidly, and then that floods the downstream communities. Or the real nightmare scenario is that the dam fills up with water, and then it's filling too quickly to safely release it, and the dam actually overtops and then has a catastrophic failure. In the case of a catastrophic failure of this dam, it's been modeled that you'd have a wall of water up to 20 feet high that would basically sweep from here to the Pacific Ocean, taking out everything in its path. Over 1 million people would potentially perish if they weren't evacuated in time. Potentially dangerous stuff. To make all this matters worse is the idea of a 100-year storm or a 500-year storm is actually based off of the way, basically the geologic record of the couple thousands of years leading up to now. Unfortunately, with climate change, those designations aren't really accurate anymore. That is to say, we can now expect a 100-year storm to happen with more than a 1% chance per year, and a 500-year storm to happen at much more than a 0.2% probability per year. That is a 1 every 500 year, 1 in 500 year chance. It's now estimated that there's more like a 1% chance a year that we could have a 500-year storm. So it's basically 5 times more likely to have one of these massive storms with the climate change. Basically, as the ocean warms up, there's more evaporation off the ocean, and it's more likely to have these really intense rainfall episodes. Now that I've passed the Whittier Narrows Dam down there in the Rose Hills, Hacienda Hills, oh, there's bunny up there. Now you can start to see the San Gabriel Mountains up ahead, off in the distance, which is where I'll be climbing into tomorrow afternoon. Okay, well, I'm finally leaving the San Gabriel River to go look for a hotel to spend the night at. It's going to be late afternoon. Okay, minor milestone here. I've now so far I've been paralleling my daily commute. Of course, I'd normally be down in the freeway down there. About 3/4 of the way towards my place of work, which would be down past those hills there. Those are the San Jose Hills, which parallel the San Jose Fault, which is a left lateral oblique fault. So it's got both a thrust sense that pushes the hills up, and it's also slipping left lateral, which is backwards compared to the San Andreas Fault. But now my route is going to diverge and head up into the mountains. So I'm not actually going to walk to work today. Morning, just leaving the Aristocrat Motel here in Baldwin Park. Nice, clean rooms. I definitely recommend the place. You know, on my way here, I actually tried to go to a different motel that was a little bit closer to my path. But they said they didn't have any vacancies, but there were like no cars parked there. So I think they just thought I was a homeless person, which I don't, well, anyway, that's a different issue. But yeah, slept well. Got some pho for dinner last night. Went to the food for less and bought up food for the next 3 days. So now just another, I don't know, handful of miles to get to the base of the mountains, and then I'll start the more natural part of the excursion today. But now I'm heading off to the IHOP to get some breakfast. I'm pretty sure the Aristocrat Motel dates back to when this street was actually Route 66, back before they put in Interstate 10 there. Random historical note, we're about a block away here from the location of the original In-N-Out Burger, about a block that way. So as we continue to walk upstream along the floodplain of the San Gabriel River, it becomes more gravelly. So generally speaking, the closer you are to the mountains, the coarser grained the sediment is going to be. So we had, if you're down like in the plains near Long Beach, you mostly have clay soils. And as you come upstream, you get to more silt and sand, and by the time we get up to here, in like, I don't know, Urbandale, I guess we are, at this point we have gravel. And so The area around here is pockmarked with these gravel pits, where they dredge up the gravel and use it mostly as a filler for concrete, but you know, road beds and stuff like that. Another random Southern California landmark across the street is the factory for Hoi Fong Foods. It's where sriracha comes from. So if you like sriracha hot sauce, this is ground zero. Apparently on the days when they're getting the fresh chilies, it smells very spicy, but I don't think it's chili season quite yet. So, okay, here we are at the Santa Fe Dam. This is the other major flood control dam I mentioned earlier. So this was built between 1941 to 1949. You can see it's a very different style of dam, the Whittier Narrows Dam. It's 4 miles long and 92 feet high. So it's a much more massive dam, whereas the Whittier Narrows Dam, because it's in the Narrows, it has to be quite as big. Okay, so I'm up here near the top of the Santa Fe Dam. We now have you can see how the dam really does rise straight up out of the city of Baldwin Park. We're getting a much nicer view of the San Gabriel Mountains up here. Look, geese and ducklings. I'm gonna try not to get attacked while walking past. Geese and goslings, I guess. It's okay. Over this way you can see another gravel pit and the local Miller factory. Still getting closer to the mountains here in the 210 freeway coming up. Lots of water up in this part of the San Gabriel River. This long bridge behind me is somewhat unimaginatively known as the Puente Largo. When it was built in 1937, it was actually the longest bridge in Southern California. It was built as a railroad bridge for the Pacific Electric Railway. That's Henry Huntington's red car line. And now it's just a pedestrian and bike footbridge, and I guess pedal bridge. I'm not sure what you call a bicycle bridge. And it was actually damaged heavily in a big flood of the San Gabriel River here in 1938. So here you can see where half of this bridge got knocked down during the major 1938 flood of the San Gabriel River, and I guess they decided it wasn't worth the money to repair it. I think maybe ridership on the red car line was already past its peak by 1938, so I guess a single track bridge was wide enough.